Shu-Heng. This is for you.
Right, of course.
All right, let's get seated down. So I have good news, which I know some of you have heard already. Oh, you immediately thought it was food. Is Tamara here? Hi, Tamara. I have something for you.
Oh, I can't eat that. Not with that attitude.
So the t-shirts are here. Many thanks to Tamara for organizing this and to everyone who participated in putting the shirt together. So Jane will be up here after Shu-Heng's lecture with the box of shirts. I know a couple of you heard that they were here and tried to get them before. I apologize. We needed to wait a little, but we're going to just distribute them systematically. If you didn't pay yet, please pay. You can pay and then get your shirt, but we'd like to have one happen before the other. And if you miss it at 12, we'll do it again at 3:15. So, all right. That being said, we are ready for the last lecture by Shu-Heng. So he will tell us a little bit more about noninvertible symmetries.
All right, thank you. I wish I was wearing that T-shirt. Okay, so this is my last lecture here. So in the previous 3 lectures, we spent a lot of time talking about Ising models. And fortunately, we also get to talk about some 4-dimensional example, the Maxwell theory, the 4D super Yang-Mills example. But let me just remind you, in the Ising case, we talk about several constructions for the non-invertible symmetry. 2 of them will be important in this lecture. The first one is from mixed anomaly. Where we start with the Majorana CFT, where there's a -1 to the f times -1 to the f left global symmetry with a mixed anomaly. And that mixed anomaly results in the non-invertible symmetry in the Ising CFT. There's another construction which we discussed 2 days ago in the 3rd lecture, where we gauge a global symmetry in half of the space-time, and hence the name half gauging. And that also leads to the same non-invertible symmetry in the Ising CFT. 1 plus 1D, obviously. Now, today, the final topic will be, why do pions decay? And we will find non-invertible symmetry in 3 plus 1 dimensional QED and QCD. And the non-invertible symmetry there can also be constructed from those 2 different constructions there. And I'll try to cover these 2 perspectives. Okay. So before we talk about pions, let's first talk about 3 plus 1D QED. And let me emphasize U1 QED with a unit charge, a unit charge, massless Dirac fermion. And the Lagrangian is in Euclidean signature. So I'll use capital F mu nu and capital A for the U1 gauge fields for the dynamical U1 gauge fields in 3+1 dimensions. Okay. All right, so this is the QED Lagrangian. Maybe this is the fourth Lagrangian everyone learns in quantum field theory classes. Famously, this Lagrangian classically is a U1 chiral symmetry. Let me denote it as U1A, where A stands for axial. I'll use axial and chiral interchangeably. So classically, there's a U1 chiral symmetry that rotates psi, by e to the I alpha over 2. Alpha is some rotation angle, and importantly with a gamma 5 matrix here. So the gamma 5 means that we are rotating the left component and the right components of the Dirac fermions in the opposite way. The factor of 2 is not terribly important. Well, it's important for the details, but it's there to ensure that our rotation angle alpha is 2 pi periodic. When alpha is 2 pi, this is a minus sign, and that's part of the gauge group and should not be confused with any possible global symmetry. This, you can easily check when the mass vanishes, is a symmetry. It's a classical symmetry of the classical Lagrangian. Now, famously, in 1969, Adler, Bell, and Jakiev found that U1 chiral symmetry is not a symmetry quantum mechanically. There's an ABJ anomaly. I'll say more in what sense that this is not a symmetry. And they were motivated by the pion decay problem in QCD. And the fact that the chiral symmetry is not really a honest-to-God global symmetry in QED and QCD explains the neutral pion decay into 2 photons. It gives a quantitative result on the dominant decay rate. So that was a beautiful story and has a lot of influences for physics in the following decades. But if you think about it, there's something very, very slightly counterintuitive. There's nothing wrong with it. I want to emphasize that. But there's something counterintuitive. So in this whole school, we talk about symmetry. And we usually celebrate when we find a new global symmetry. We can use the new global symmetry to do anomaly matching and do all kinds of good stuff. In the story of ABJ, it's completely the opposite. You thought there were a naive global symmetry of the classical Lagrangian, and they came along and told you, no, it's not a symmetry. So how come we can learn so much from the absence of a global symmetry rather than the presence thereof? Again, I emphasize that there was absolutely nothing wrong with the original argument. And one way to make it precise is that in the real world, the fine structure constant is so small. So you can effectively treat the anomaly as a 't-Hooft anomaly. And then it's just an anomaly matching argument. But wouldn't it be nice if we can reinterpret this result in terms of the presence of a generalized global symmetry? And that's going to be the content of this lecture. All right. Another motivation for this lecture is that you can go around and ask people this question. Is U1A a symmetry of QED? This is a yes or no question. And the worst possible answer you can expect from a yes and no question is that the answer is yes and no. And let me say Why yes and why no? Well, it's no, related to the fact that there's no conserved current, as we will discuss soon. That's the content of the anomaly. But on the other hand, there are still consequences of the chiral symmetry. For instance, if you just scatter electron and positron all day long, you'll find that the scattering amplitudes respect the helicity conservation. And that follows from the classical chiral symmetry. So there are still consequences. Helicity conservation. But somehow it doesn't follow from an honest-to-God global symmetry. Again, I should emphasize that the traditional way of explaining it is perfectly correct. And let me just quickly review that. The anomaly was mediated by the instanton. In the case of U1 QED, there's no instanton in flat spacetime. Instanton. Because pi 3 of U1 is trivial. So if you are a flat spacetime person, and if you only care about electron and positrons, the anomaly doesn't hurt you. It still leads to good conservation law and selection rules. But it's kind of saying that the U1 symmetry is only a symmetry of QED in flat space. That sentence is technically correct, but philosophically, it's kind of against the way we think about global symmetry these days, and quantum field theory more generally. When we think about quantum field theory, one very nice thing about quantum field theory is that it comes with a stress energy tensor. And using the stress energy tensor, we know how to couple the quantum field theory in a general geometric background space-time. So we shouldn't, when we think about quantum field theory, we shouldn't just restrict ourselves to a particular background. We shouldn't just restrict ourselves to flat space-time. This is particularly important when we talk about dualities between different quantum field theories. And global symmetry plays the role of some kind of ID number for different quantum field theories. When we try to say that two seemingly different quantum field theories are actually dual to each other, are actually the same as each other, we try to match their global symmetries. And we want to do this match on general permissible background geometry. And we should think about global symmetry as an intrinsic ID number for the quantum field theory, not sensitive to what background you put it on. The global symmetry can behave in a funny way depending on the detail of the background. But whether or not the quantum field theory has a symmetry shouldn't depend on that. And that's another motivation for this lecture, where we are going to provide the alternative straight answer to this question. All right. Any questions for the introductory part? All right. If not, let's get started. So I'll start with QED. So in QED, you can define current. A stands for axial in the following way. The factor of 2 doesn't matter that much. It's just that factor of 2 over there. This current is trying to be conserved, but quantum mechanically, as shown by ABJ, it's not quite conserved, but obey the following anomalous conservation equation. So I'm writing everything in the differential form notation. JA is treated as a 1 form. If you compare this equation with the one you found in textbooks, the normalization is slightly different. I normalize my field strength 2 form so that when you integrate it on any 2 cycles, it gives you 2 pi times the integer. Sometimes people might normalize the field strength by a factor of the electric coupling, and then you get a factor of E squared over there. But here we prefer not to do that. All right, so I'm going to take this as given which was worked out by ABJ, and see if we can derive a conserved quantity. That's what we mean by symmetry. Now, the first thing you will try is just to define an operator U alpha supported on some 3-manifold M as so I alpha integral of M star JA. Now, this is a sensible operator. Of course, you have to be a little bit careful in expanding the exponential, taking care of the UV divergence when pairs of JA are close to each other. But you can try to do that. The bad news is that since star JA is not a closed form, since the right-hand side is not 0, this is not conserved. I'm going to use the word conserved and topological interchangeably. So as we discussed in the first lecture, you should think about the word topological as a suited-up version for conserve. Okay, so that attempt fails. The second attempt, which I would like to give credit to Adler, it was already in his 69 paper, was to define an operator, which I'll put a little hat on there in the following way. So what was his trick? His trick was that, well, even though this is not a closed form, f wedge f can be locally written as ADA. So why don't we just move this term to the left-hand side and shift the integrand here by the ADA 3 form. So JA is a 1 form, star JA is a 3 form. It makes sense to take linear combination of star JA with this 3 form. This form was later known as the Chern-Simons term. But note, interestingly, that Adler's paper was in 69. And Chern-Simons' paper, I think, was in the 70s. Okay, so the thing in the parenthesis, this guy over here, is formally closed. If you take the exterior derivative and use this equation, this is closed. So this is formally conserved. But I'm going to put quotation marks around this expression. And the reason I need to put quotation marks is that this operator is actually not gauge invariant generally. And this is a fact that John has used extensively in his lectures, and I think Meng also mentioned that. So here I'll just say it as a fact that the Chern-Simons action, or more precisely the exponentiation thereof, is gauge invariant, in particular invariant under the large gauge transformation, if the coefficient n here is an integer. The coefficients over here is not an integer. Is I alpha over 8 pi squared. Alpha is any angle between 0 to 2 pi. So generally, this is an improperly quantized Chern-Simons term. And therefore, by this fact, it's not generally gauge invariant. Now, for the experts, let me add that since QED is a theory of fermions, I'm going to assume the manifold is a spin manifold. And therefore, the 3-manifold M here in our space-time, I'm also going to assume it to be spin. It's a simplification that makes our life easier. You can probably relax the tangential structure, but I'm not going to do that. All right. All right, so that's the bad news. This is not gauge invariant. This, for whatever it's worth, is gauge invariant, but it's not conserved. And that was the status at 69. You either have a gauge invariant operator that's not conserved, or you have a formally conserved operator, but it's not gauge invariant, so I don't know what I'm talking about. And that's why I put it in quotation marks. So at the end of the day, we didn't find a gauge invariant conserved quantity. And hence the statement that the U1 chiral symmetry is not a global symmetry quantum mechanically. All right, any question at this point? Great. Now, to make progress, let's first be less ambitious. So this is trial number 3. Let's be less ambitious. Instead of taking a general alpha between 0 to 2 pi, let's take alpha to be 2 pi over n, where n is any positive integer. So we restrict our attention to some discrete rotation of the classical chiral symmetry. I'm going to rewrite that problematic operator, keeping track of the quotation marks. What am I having? 2 pi I over n star ja, and that's going to be minus, oops, I'm going to use my red chalk. Minus I over 4 pi n ADA. Okay. But it's still in quotation marks because the red term is still not gauge invariant. Right? The n here is in the denominator rather in the numerator. So we didn't solve the problem. A side comment. If your Dirac fermion has higher gauge charge, 2, 3, or 4, or if you have multiple species of Dirac fermion, you will modify the coefficients here to be some more general integers. And then here, you can make this properly quantized by choosing the appropriate n. And that's the familiar statement that if you have multiple species of Dirac fermion, the ABJ anomaly doesn't completely break the U1 symmetry. Rather, it breaks it to some discrete invertible subgroup. But here, let's do the minimal case. You have a single Dirac fermion unit gauge charge, in which case you are not left with any discrete subgroup. Okay, so far we haven't achieved anything. But if you recall, in John's lecture, this term actually appeared in a completely different context. So we are going to have a little detour here. Yeah.
This is fine for n equals 1 or -1.
Yes, for n equals to 1, so the question was, what happens when n is 1? Or -1. Now, when n is plus 1 or minus 1, alpha is 2 pi, and that's a trivial rotation. So it is fine, but it is a trivial operator, unfortunately. Okay. Any other question? Good. So let's recall John's lecture. This term appeared in John's lecture in the context of a completely different quantum system, the 2 plus 1D fractional quantum Hall state. Fractional quantum Hall effect. There, this red action was used as an effective action. So let me just write it again. So in that context, M is some 2 plus 1D space-time manifold for the physics of fractional quantum Hall state. And this was used as the effective action to describe the nu equals to 1 over n fractional quantum Hall state. In that context, capital A is not a dynamical gauge field. It's the external background gauge field you turn on. It's the gauge field that's responsible for the large magnetic field that you turn on when you perform a fractional quantum Hall experiment. So I drew a line between the two to distinguish the difference in these two quantum systems. If you recall, in Zhang's lecture, we didn't start with this. In fact, let me put it in quotation marks as well, because it's not properly quantized. But in Zhang's lecture, we didn't start with this. We started with something else. Do I have a blue chalk? The action we started with was the following. Where there's an additional dynamical little a gauge field. And what Zhang did was formally integrate out little a and obtain a relation that little a is minus capital A over n. If you substitute this relation here, you go back here. But let's compare these two actions. This one is in quotation marks, this one is not. This one is not in quotation marks because every term are properly quantized based on the fact quoted there. So the blue action is perfectly gauge invariant. To be more precise, the exponentiation of the blue action is perfectly gauge invariant under large gauge transformation. But the red one is not. So how come we can relate the two? That is because in relating the two, this relation is only true locally. Both little a and capital A are properly quantized gauge fields, which obeys this quantization condition. And you cannot equate a properly quantized gauge field to another one divided by an arbitrary integer. So this is to be expected. There's no legal manipulation that can relate a gauge invariant action to a gauge non-invariant one. Having said that, this red action is still very useful and powerful. It describes a lot of beautiful physics, but it misses some global aspects of the physics. And the blue one should be thought of as the more precise and gauge invariant version thereof. So that was the story in Zhang's lecture. It's in 2+1D. It's a tabletop experiment. But motivated by this discussion, we can now go back to the 3+1D QED and construct a new operator. And by now, it should be clear what we are about to do. We're just going to replace the red term, which is causing us a lot of troubles, by the blue one. So back to trial number 3 in QED. We define the following operator. D, it has a subscript 1 over n. It's defined on some 3-manifold M. Now, okay, let me first write it here. But here comes the question. What is little a in the universe of QED? In QED, we started with capital A, which is our dynamical U1 gauge field, which is the fields for the photon. JA contains the Dirac fermions. And those are all the fields and states we have in QED. You can scatter electron with positron, with photon, etc. You don't have this little a. This little a is only an auxiliary field that we introduce on this 3-manifold in the whole 4-dimensional space-time to define this operator. So that's why what this path integral represents. It's a path integral over an auxiliary field, little a. The subscript m means that little a only exists on the support of this operator D. It doesn't exist asymptotically away from the operator. So you don't change the asymptotic state of your QED. You quantize your QED on some three-dimensional slice, you still only get the electron state, the positron state, and the photon state. Yeah, there was a question.
Aren't you just introducing small a, so you have a new degree of freedom that can make everything gauge invariant?
So the question was, should we think of little a as the additional bulk degrees of freedom to make D gauge invariant? You might be able to do that, but I don't want to do that. I don't want to change the bulk. Right? The name of the game is that I'm working with the good old-fashioned QED that Schringer, Dyson, Feynman work on. I don't want to change the asymptotic state, but I want to identify a new conserved and gauge invariant operator. And this little a, you should think about it as some kind of impurity that's localized somewhere in your space-time. And its sole purpose in life is to give you a gauge invariant and conserved operator. Yeah.
I was also thinking in lines of what you say. Isn't this equivalent to kind of sum over all gauge transformations? So you start with your gauge non-invariant operator, and you like sum over all gauge transformation, so you get a gauge invariant object?
The question was, can we think about the path integral over A as summing over the gauge orbit of our original gauge non-invariant object? I think there's a difference between the two. In fact, there was a paper trying to do that by summing over the gauge orbit. The difference is that if you take that perspective, you can do it for any alpha, not just 2 pi over n, not just rational alpha. That's one difference. The second difference is that there's no guarantee if you do the summing over orbit or integrating over orbit will give you a well-defined defect. And that's what we emphasized in the first lecture. Here I'm presenting it so far as an operator, but we also want it to be a well-defined defect associated with a well-defined Hilbert space. And this construction will, as I will discuss later, guarantees that it's associated with a well-defined defect associated with a well-defined Hilbert space. The reason is because what I'm doing is to stack a 2 plus 1D TQFT, namely the fractional quantum Hall state, to this operator. And the fractional quantum Hall state is a local TQFT associated with a good Hilbert space. I will also briefly comment on the construction from half gauging, which, as we discussed last time, manifestly give you a well-defined defect. Yeah. Any other questions? Yeah. Sorry, say again?
Can you do this in other dimensions?
The question was, can we do this in other dimensions? And the short answer is yes, and there has been a lot of papers on that subject. You can do it in other dimensions. You can do it for higher form symmetry as well. So there has been applications or generalizations of this construction to axion physics in 4D, also to some higher form symmetry in 11D supergravity. So there are all kinds of generalization. Yes. Any other questions? Great. Okay. So what do we have so far? This new operator D in QED is gauge invariant because all the coefficients here are properly quantized. A more non-trivial fact that it's also conserved. And I'm going to explain that very quickly here without giving too much details. And that is the half gauging construction. So here I derived the operators, just kind of, I was motivated by fractional quantum Hall state. It seems completely disconnected to the previous lectures. One connection is that we did start with the anomalous global symmetry. And let me be a little bit more precise on that. I started with QED, but you can forget about the gauge fields for the moment. If you forget about the gauge fields, you are just working with the free massless Dirac fermion. In the free massless Dirac fermion, there's a chiral symmetry, and it's an honest-to-God good global symmetry. It also has a vector symmetry, U1V. And there's a triangle 't Hooft anomaly between them. In the free Dirac fermion theory, this is a 't Hooft anomaly. Both U1V and U1A are honest to God global symmetry. The only pathology of having a 't Hooft anomaly is that when you gauge one of them, the other guy becomes weird. And that's the same status as in the free Majorana CFT. The free Majorana CFT has a -1 to the F, -1 to the F left symmetry. Both of them are honest to God global symmetry, but they have a mixed anomaly. Here in QED, U1V is gauged. And we did see something funny about the chiral symmetry. It turns into this new object, which later I will argue to be non-invertible. So that's the first perspective of viewing this non-invertible symmetry in analogy with the Ising model. Now I'm going to talk about the second construction via half gauging. I'm going to be a little bit brief. It's a little bit technical, but I think it's worthwhile mentioning it at the school in particular. So QED, so as we discussed last time, in 3+1 dimensions, if you want to run the half gauging construction, you don't want to work with a zero-form symmetry. You want to work with a one-form global symmetry. Now, what one-form global symmetry do we have in QED? In Maxwell theory, before coupling to the Dirac fermion, you have an electric one-form U1 symmetry and you have a magnetic one-form U1 symmetry. The moment you couple the free Maxwell theory to Dirac fermions, you break the electric one-form symmetry. But here we didn't include the magnetic monopole. There's no dynamical magnetic monopole. So the magnetic one-form symmetry is still intact. So the QED has a magnetic U1 one-form global symmetry. But if you recall, the last lecture, we always use a discrete one-form symmetry to run the argument. That is because only for discrete one-form symmetry, you can construct a topological Dirichlet boundary condition and thereby a topological defect. So U1 is a little bit too much for us. But you should never complain when you have too much. You just restrict your attention to a subgroup. So the hero of the story is the Zn one-form magnetic symmetry of the QED. And you can show that when you take QED of the Dirac fermion, and you can couple to the magnetic one-form symmetry. So I'm going to write a dynamical gauge field for the magnetic one-form symmetry as little b. So this little b is a two-form gauge field that couples to the magnetic one-form symmetry. And if you recall from Thomas' lecture, the current for the magnetic one-form symmetry is just a magnetic field, namely F mu nu. So this is the minimal coupling between the dynamical gauge field to the current of QED. And of course, we have to make little b a Zn value field. So you have to introduce a one-form gauge field C, whose sole purpose in life is to make B Zn value. In the lecture from 2 days ago, I think I called it an ADB. So A and B and C are kind of reshuffled here. But that's unavoidable because we need to use the little a for this little guy. Anyway, those are just notations. But then there's one more key ingredient, which I emphasized on the lecture from 2 days ago. When you gauge a global symmetry, there are options. And here the options are important. You actually have to add a term of the following form. So maybe I should use the same color coding. So don't worry about this term too much. It's just to make it Zn value. This is the coupling to QED. This is an additional term you can add. This is a term that's just made out of B with some particular coefficient. Okay. What I'm not going to do in real time, in fact, you can kind of do it in real time, is to show that this coupling will actually give you QED itself, but with the theta angle. So recall that we have a gauge field. We have a abelian gauge field. The abelian gauge field can have a theta term. We didn't start with the theta term. The reason is because we have a chiral symmetry, and you can do the chiral rotation to get rid of the theta term. But if you do this gauging, it actually generates a theta term shift for you. It shifts theta by minus 2 pi over n. And let me just say intuitively why that's the case. Forget about this unimportant term. Integrate out little b as careless as you could. Then you generate the f wedge f term. And that's exactly the theta term. You have to do it more carefully because the whole topic was about how to properly quantize the coefficient. So you have to do it properly. And I can give references later on, but that's the rough intuition. So what do we have? We take QED, we gauge the Zn magnetic one-form symmetry, importantly with the choice of the discrete torsion. And what we end up with is QED with a shifted theta angle. But there's no difference between QED with massless Dirac fermion with a shifted theta angle or without a shift. The reason is because ABJ, or I think more precisely Fujikawa, taught us that if you have a massless Dirac fermion, if you perform a classical chiral rotation, which you can think of it as a field redefinition, it shifts the theta angle. So the result you get is isomorphic to QED itself. And then we are in good shape. If you recall the lectures from 2 days ago, I can perform the half gauging construction whenever the quantum field theory, after gauging a global symmetry, is isomorphic to the original one. Okay? And with a little bit more work, you can show that this half gauging precisely gives you the operator D over here. Yeah, John. The question was, what would I get if I had not added this term? The answer I can give is that it doesn't give you back the QED. I don't know the answer on top of my head. I mean, it could. I think it just rescales the gauge field by some amount. Let me not make a commitment on the spot. What I can say for certain is that it doesn't give you the QED. Okay. Any other questions? Great. Okay, so hopefully I have covered the two perspectives on how to construct this D operator. And let me make a final comment. Because I can construct it using half gauging, this is topological. That's the power of the half gauging construction, and thereby explain the conservation. Okay, so far it sounds like this is all good news. You know, we work with this good old-fashioned QED, we find a new gauge invariant and conserve quantity. But there's no free lunch in theoretical physics. And let's look into this D in a little bit more details. Okay. So, already anticipated, D is non-invertible. The quickest way to argue this is that I use a fractional quantum Hall state on my operator D. Fractional quantum Hall state, by definition, is a non-invertible topological phase in condensed matter physics, so it cannot be undone. Okay, that's a highbrow argument. So let's try to see it in more details. At least let me show that. So if something is non-invertible, in particular, it's not unitary. Unitary matrices are invertible matrices. And therefore, if it's non-invertible, it's in particular non-unitary. Okay, so how do we check if something is unitary? We treat them as operator. And what you do is just multiply D with its dagger. Okay. If it's unitary, you get 1. So what do you get? Well, let's take that expression over there. And whenever you see an I, you flip the sign of I. That's what dagger does. Now, there's one little thing that's new here, which is that for every such operator, for each of D and D dagger, you have to have a separate auxiliary little a gauge field. I'm going to denote them by D by A and A bar. And let me emphasize that A bar does not represent the complex conjugation of A. Bar is just part of the name. So you have a little a for D, you have a little a bar for D dagger. They are different. They are both dummy variables. The first term over here will get canceled when you multiply D with D dagger because it doesn't see A or A bar. But these two terms will behave in a funny way. But it's not too hard to collect them. You literally just repeat it with a minus sign. All right. Now, this is a mouthful. This seems like a complicated operator. But the only thing you need to know is that it's not 1. And therefore, it's not a unitary operator. But since this is the school, and we talk a little bit about the condensation defect, so I have to make this comment. The right way to think about the operator on the right-hand side is that it's a condensation defect. In fact, this is the condensation defect from the Zn magnetic one-form symmetry over there. You should think about this C as the analog of 1 plus eta in Ising. Now, in what sense this is 1 plus eta in Ising? Let's look at it. Little a and little a bar are dummy variables. You're path integrating over them. So at the end of the day, they don't have a physical meaning. Capital A was our U1 dynamical gauge field. D capital A is just the magnetic field. So what are we doing here? We're doing something very complicated on our magnetic field. If I hand you the magnetic field, what's the first thing you do? You take your dA, namely capital F, integrate it on a 2-cycle, on a sphere. What is that? That's the magnetic flux. Magnetic flux is defined on a 2-dimensional sphere. But we're not doing that here because M, importantly, is a 3-manifold. So it's like you are trying your very best to define a magnetic flux on the 3-manifold. Why does that thing make sense? It actually makes sense, and that's the purpose, that's the whole point of condensation defect. If you recall yesterday, well, not yesterday, 2 days ago, we have an expression like this. This is in Maxwell. In free Maxwell, you can take eta, which can be the electric one-form symmetry or the magnetic one-form symmetry. Let's take it to be the magnetic one-form symmetry. Then eta is nothing but the magnetic flux through the 2 cycles S. But the input is a 3-manifold. And what you are doing here is just to look through all the non-trivial 2 cycles in your 3-manifold and take a sum over them. There's some difference between here and here. There will be some additional phases coming from the discrete torsion related to the phase that John was asking about. But qualitatively, it's the same. So you should just, that's a little bit abstract. It's worked out very carefully in the literature. But let me just say that you should think about this as some kind of magnetic flux through a 3-manifold. Yes?
Is there something mathematical about it that I can just see that it can't be 1?
So the question is Is there something mathematically about it that you can see that it can be 1? That's a great question. The first answer I will give is that, well, it doesn't look like 1. That's the most irresponsible answer I can give. Yeah. Now, and now let me give a better argument later on. Okay. Remind me if I don't, because I actually didn't prepare that in the lectures. But when I talk about how it acts on various operators, it will become clear that this cannot possibly be 1. Any other question? Yeah.
So it's clear that if you fuse two things, you can make from half gauge and get a condensation defect. But is the opposite true? If I fuse things and get a condensation defect, were those defects always constructed by half gauge?
The question was, if I construct something, so this was actually a question that could be asked in the last lecture. In the last lecture, we talk about half gauging, talk about non-invertible symmetry from half gauging, namely D, extensively, and we showed that D times D bar will be C. The question was, if you have something such that its product with its complex conjugate is a condensation defect, does that necessarily mean it comes from half gauging? The short answer is I don't know. I don't have any counterexample in mind. But I also don't know how to prove it rigorously. Yeah. Any other questions? Okay. Okay, so we have established that we have a non-invertible symmetry in the good old-fashioned QED. Now let's try to understand it better. So now let's discuss how it acts on the various operators and fields. So first, the non-invertible symmetry, oh, sorry, I should make another comment. I forgot. So this is for alpha equals to 2 pi over n. But you can easily generalize it to 2 pi p over n, where p and n are coprime. So in this way, you get d p over n. Where p over n is a rational number. You have to mod it out by z, because if you shift it by integer, it doesn't do anything. So what we have concluded is that U1 chiral symmetry is not completely broken by ABJ. The rational part of the chiral rotation can actually be resurrected as a non-invertible symmetry. And at the level of the slogan, you use a fractional quantum Hall state to cure the ABJ anomaly. And if you look back in history, it's kind of interesting. So Adler's paper was really fantastic that he talked about this U-hat operator carefully. But there was no way that ABJ could have discovered the non-invertible symmetry back in 1969. The reason was because the cure, namely the fractional quantum Hall state, was not discovered until 1982. Okay. All right. So now let's talk about the action of this non-invertible symmetry. You have a rational worth of non-invertible symmetry, how it acts. Now, the first obvious fact is that dp over n acts invertibly on the fermions. This is because all these blue terms in D, it doesn't talk to the fermions, and the fermions only experience the action from this part. Another way to say it is that here we do half gauging. And the half gauging is the gauging of a one-form global symmetry. Local operators are not sensitive to one-form global symmetry. And the only parts that the fermions got acted by is that in the last step in the isomorphism, we have to do a chiral rotation. And that's an invertible action. So the fermions, the electrons, the positrons, they just got acted invertibly. It's the most naive action you might have expected from the classical chiral rotation. And that is why the positron and electron scattering obeys the helicity conservation. You can now think about it as selection rules from the non-invertible symmetry. And it is an exact global symmetry of the QED. But what's non-invertible about it? So you should think about this part as the analog, as in Ising, where if you have a non-invertible symmetry, the way it acts on the epsilon operator is just by a minus sign. And you don't see anything non-invertible if you only look at the thermal operator. Then what is the analog of the older operator in QED? And that's where it gets interesting. It acts non-invertibly on the monopoles. I should be more precise by what I mean by monopoles here. I emphasized in the very beginning that we don't have dynamical monopoles. And here by monopoles, I mean a two-hoop line. It's a line defect in space-time that represents extremely heavy monopole whirl line. And you can already expect why the non-invertible symmetry acts non-invertibly on the monopole whirl line. The reason is because we constructed it from half gauging. And what symmetry were we gauging in that construction? We were gauging the magnetic one-form symmetry. What are the charged objects under a magnetic one-form symmetry? Thomas told us those are the two-hoop lines. So it's the two-hoops line that got affected. So the picture is that if you have a non-invertible symmetry dp over n here, and you prepare a two-hoop line, so I'm drawing this in space-time. If you prepare a two-hoop line h on the left, and you bring it past the non-invertible symmetry, then what you end up with so what will happen to the two-hoop line is that it experiences a Witten effect. In the half-gauging construction, we say that the gauging, the net effect of the gauging is that you shift the theta angle. And then we have to do a chiral rotation to go back. The shift of the theta angle doesn't do anything on the fermions, but the chiral rotation acts invertibly on the fermions. For the two-hoop line, it's the opposite. The chiral rotation doesn't act on the two-hoop line, but the shift in the theta angle does something funny to the two-hoop line. And that has a famous name. When you have a monopole and you shift the theta angle by a certain amount, note that I didn't shift the theta angle by 2 pi, right? I shifted by 2 pi over n, or more generally 2 pi p over n. If you shift theta angle not all the way through, there's a famous effect known as the Witten effect that told us that the monopole becomes a dion. Importantly, theta is not shifted all the way by 2 pi. And therefore, the electric charge obtained by the monopole is fractional. So on the right-hand side, we get a dion with fractional electric charge. But what is a dion with a fractional electric charge? It cannot be a genuine whirl line in space-time. It should be thought of as the boundary of a surface defect. This is the same as saying that a dion with fractional electric charge is not mutually local with a 't-Hooft line, and therefore it's attached to a branch surface, and that is this blue object. And in fact, this blue object is exactly the magnetic one-form symmetry we were talking about. So this is exponential 2 pi I, sorry, not 2 pi I, IP over N F. So how do you think about this? F is a well-defined local operator. You can integrate it on a surface. F locally is dA. So you are very tempted to write this as a line integral over here with coefficient P over N. But that's not a properly quantized Wilson line, and it's not a genuine line operator. And this is a precise expression for a fractional Wilson line. And it's multiplied by the original 't-Hooft line over here.
Yeah.
Yeah, so it's integrated over this surface of the tube. Huh? Sorry. The what?
The integral sign is missing.
Oh. Thank you. Okay. And this is the analog of in Ising. I'm sorry, I'm writing this really small. In Ising, if you have a non-invertible symmetry and you start with a sigma operator, this is a picture we have seen many times, so I hope it's okay. I'm writing it very small. This is the same as in Ising. If you start with an order operator, it becomes disorder as it passes through the non-invertible symmetry. But now the monopole is playing the role of the order operator, whereas the dion is playing the role of the disorder operator. Great. Now coming back to Oliver's question, how do I see this is now 1? One way to see that is when you prepare a Hilbert space with non-trivial magnetic flux. Then this D will annihilate it. It's the same kernel we saw in Ising model where D annihilates the state created by the order operator. Similarly in QED, if your space has a non-trivial 2-cycle, you can insert a flux in that 2-cycle and prepare a state. And D as an operator has a kernel on it, and therefore it cannot possibly be unitary or invertible. Okay. So, so the non-invertible symmetry is particularly interesting when you have a monopole, and it has interesting applications in the monopole fermion scattering problem, and that's historically known as the Kalin-Rubakov effect. And there has been some recent interesting papers on this subject. Yeah, so there was.
Is there any restriction on n if you have time reversal symmetry?
The question was, is there any restriction on n if I have time reversal symmetry? I'm not sure. Yeah, go on.
I think like the wind effect only gives you like monopoles that carry charge 1/2.
QED does have time reversal symmetry here. Well, it doesn't play any role in my discussion. I mean, there might be an interesting algebra between them, but I'm not sure. I don't think it doesn't ruin the construction here, but there might be an even more intricate structure. In fact, later on there was a paper we talked about non-invertible time reversal symmetry. Maybe that was more closely related to your question. I don't know. I'm not sure. Okay, thank you. Yes.
The dion has to be the boundary of the surface. Is there a reason that that surface has to end on a defect and can't form like a disk?
Oh, that's a great question. I think in this case you can actually, so the question was, in what sense this surface is attached to the non-invertible defect? I think in this case you can actually peel it off and make it a solid disk. I'm drawing it this way in analogy with the Ising case.
Is there a magnetic dual of this?
No, because so the question was, is there a magnetic dual of this? The short answer, I'm not exactly sure what you mean. The short answer is no, because QED doesn't have electromagnetic duality. It has fermion, but no monopole. It has dynamical fermion, but no dynamical monopole. So electric and magnetic are on different footing from the get-go. If you go back to free Maxwell, then there's an interesting spectrum of non-invertible symmetry transforming to each other under the electromagnetic duality. Oh, yes.
Is there a sense that I can formally take n to infinity and claim that I recover the full U1?
The question was, is there a sense I can take n to infinity and recover the full U1? The short answer is, I don't know. I mean, it is what it is. You have a Q mod Z symmetry. Rational numbers are dense in U1. I think that's the best you can say. Yeah. I mean, you can to be large. You can take n to be however large you want, and that will give you a non-invertible symmetry. So the question is, does it still don't have the conserved current? That's an excellent point, and let me just emphasize that again. We do not have a conserved current, right? We didn't resurrect the current. In fact, we didn't even resurrect the charge. The integrand here is not gauge invariant. This whole thing is not gauge invariant. It's still shifted by some 2 pi times I times the integer under large gauge transformation. The only thing that we rescue from this whole ABJ anomaly was the whole symmetry operator. It's this object after the exponentiation. In fact, you should think about the path integral as the sophisticated version of the stupid non-invertible symmetry we talked about in the first lecture, where we just sum 2 operators together. There we take 1 and we take eta, and we say, oh, that's a projection, and that's non-invertible, great. But that was stupid, because 1 and eta are individually well-defined. Here it's not the same. If you fix a configuration for little a, this is not a gauge invariant operator. Only after you do the path integral, it becomes gauge invariant. You should think about this as an infinite dimensional version of doing that sum, except that this here is not stupid. Okay, any other question? Yes, oh, sorry.
I was just going to say we've got about 8 minutes.
Okay,
So
yeah.
I want to talk about
Yeah,
planets.
oh yeah.
This might be very stupid, but if A and A bar were non-dynamical, couldn't you just fix them to be equal at all times?
The question was, can A and A bar be non-dynamical? The answer is no. You have to make them dynamical to obtain a gauge invariant operator. Yeah, that's related to my previous comment. Fix a particular field configuration for little a. This is not gauge invariant. So I was warned by Oliver that I should move on to pions. That will be very quick, because we basically have everything set up for us. And as I'm erasing the blackboard, let me just make one comment on naturalness. You can ask, so 't Hooft has a notion of naturalness. He said that if you have a Lagrangian with some global symmetry, then global symmetry G, you should write down every G invariant term with order 1 coefficient. That's 't Hooft's notion of naturalness or technical naturalness. In what sense is the massless QED Lagrangian natural? What's the symmetry that forbids you from writing down the electron mass term? The conventional answer, which was actually the answer in 't Hooft's 1980s paper, is that it's a chiral symmetry. But 't Hooft, of course, knew of the ABJ anomaly. So he added a little sentence after that discussion and said that here you don't have to worry about the ABJ anomaly because we don't have instanton in flat space-time. That's perfectly correct, as I emphasized throughout the lecture. But now you have a better way of saying it. Well, not necessarily better. You have another way of saying it. You can say that the massless QED is natural because of the non-invertible symmetry. Okay, so in the remaining 6 minutes, let's talk about QCD. I'm going to work with the massless QCD below the electroweak scale. And therefore, I have a U1 electromagnetic gauge symmetry. Now in QCD, in this limit, QCD has a classical global symmetry, which I'll call U1A3. It rotates the up and down quarks in the following way. there's a sigma 3, meaning that you are rotating up and down in the opposite way. If you drop the sigma 3, that would be the global symmetry corresponding to the eta prime particle. Unfortunately, I have nothing clever to say about eta prime. This is a classical global symmetry, but it has the triangle anomaly with the electromagnetic gauge symmetry. And it's anomalous in the same way as the chiral symmetry in QED. So we don't have to do any more work. Just run the machinery again, and then you obtain all the non-invertible symmetry, P over N, in QCD. And let me emphasize that this is the symmetry associated with the neutral pion. Okay? Now the question that ABJ asked in 1969 is that QCD going to the IR flows to the pion Lagrangian. And now we are saying that there's a non-invertible global symmetry in QCD. If we have a global symmetry in the UV, we better try to match it in the IR. So how does the pion Lagrangian match the non-invertible global symmetry? Well, I should make another comment that the massless QED is natural because of the non-invertible symmetry. And that's another reason why there's no Coleman-Weinberg mechanism in fermion QED. You start with a massless fermion, you do loops, you are never going to find a mass for the fermion. In contrast, for the scalar QED, there's no enhanced symmetry at the massless point. And that's why you have a Coleman-Weinberg mechanism. Okay, coming back to pions. The relevant term for us in the pion Lagrangian will be the kinetic term for the neutral pion plus a coupling between pi 0 and f wedge f. For all I know at this point, G could be 0. The question is, how does this Lagrangian match the dp over n symmetry in the UV? That's a very interesting calculation. I don't have time to do. It's in the literature. I can give you the references later. Let me just sketch the calculation. You insert your dp over n, let's say at x equals to 0. And in the bulk, you just have your pion Lagrangian. And this is a very simple system. What are the fields you have? You have pi 0. It's a compact scalar field. Periodicity is set by the pion decay constant. You have the dynamical U1 gauge field, capital A, and you have little a that we introduce only at x equals to 0. So you have 3 fields. That's it. And you should just go ahead and derive their equations of motion. It's an interesting equation of motion because you have contribution from x away from 0 and contribution from x at 0. And you have 3 equations. And it's a simple calculation to show that the 3 equations are only consistent if G is 1 over a pi squared f pi. And that's exactly the correct coefficient in the pion Lagrangian that will give you the correct decay rate of pi 0 to gamma. So in a maximally offensive manner, you can say that the neutral pion decays because of the non-invertible global symmetry. All right, I have 1 minute left. I'll probably won't. Let me just make one final comment. So there's a similar construction in axion physics. And there, it leads to explanation of how you should think about the so-called page charge. Page charge is a gauge non-invariant charge discussed commonly in supergravity. The right way to think about it is very similar to here, that you never have a gauge invariant charge. The non-invertible symmetry is a resurrection of the symmetry operator. In that context, in the context of axion, you can also construct such a non-invertible operator. And it's a precise version of what is known as the page charge. And one very interesting application of that non-invertible symmetry in axion physics is that it gives you universal inequalities between the mass of the electron and the monopole. So recall that in the previous lecture, we said that the non-invertible symmetry is subordinate to the invertible symmetry. Right? In the Ising case, D is subordinate to the Z2. We use Z2 to construct the D. So when you break them, you cannot preserve the non-invertible symmetry while breaking the Z2. And that order between them gives you inequalities in axion physics. And it tells you universally that electron has to be lighter than a monopole. Okay, so I think that's almost everything I want to say. And the last thing I want to comment is this part of the blackboard, which I really like. You see, on the one hand, we have the Ising model in 1+1D. On the other hand, we have QED in 3+1D. But they actually share a lot of similarities, despite the fact that they are very different quantum systems. And I think that's really the beauty of symmetry. Thank you.
Questions for Shu-Heng? All right. Well, if not, I just want to remind you, as we thank Shu-Heng again, that he's delivered not only this great series of lectures, he was also one of the scientific organizers for this school who put the program together. Let's give him a big round of applause.
Thank you. Yeah. Well, and also many thanks to Oliver, Ethan, and Tom. I don't think Jen is here, but also to Jen for the local committee here for putting together this really wonderful school. Thank you.
Thank you, Shu-Heng. So I know where Jane is. Jane is outside with the box of T-shirts. And we will bring her in here after the last lecture so we can thank her one more time. But for now, if you want to pick up your T-shirt, please go ahead and do it. Pay if you have not paid, and we'll see you for the last lecture at 2. These are wonderful lectures.
Thanks.